So, this is very important slide, this one. I have grouped here analysis methods as different classes. Radiometric methods in the left, then microanalytical methods and some other methods. So, what is the advantage of using radiometric methods? So the point is that radionuclides, they actively send us information about when they decay. So we do not need to kick them and say that please send us information. They do it actively. And we can use, for example, direct or non-destructive alpha spectrometry. We can use gamma ray spectrometry, beta spectrometry, X-ray imaging or spectrometry imaging or fission track methods. We can use these without activating the nuclide itself. They actively send us information. What about microanalytical methods? We have to say to nuclides that please send us some information. Okay, I cannot say them that please send us information. I have to use protons or electrons or different kind of particles so that they can send us information. Methods are, for example, neutron activation. Particles are then neutrons. We can use X-rays. We can use electrons. And in fact, this SIMS is one part of mass spectrometers. So I think it's quite important to understand the difference between these two. So they actively send us information. We have to say to nuclides that please send us information. And then there are some other type of methods like mass spectrometry or liquid scintillation methods or infrared spectrometry or whatever are the methods. And in this course we use these methods and also a little bit these methods too. Okay. So as I explained, I will explain this once more. Advantage of the radiometric methods, such as alpha or gamma spectrometry, is that we do not need to wake up the material we are analyzing. They automatically send us information. And if you want to calculate the activity, you will see this equation many times during this course. But we can calculate the activity in a very simple way. And this equation holds for gamma spectrometry and alpha spectrometry. So we have to determine peak area. We have to know efficiency of your detector. We will consider these parts later. We have to know now the nuclear data. And we have to know the measurement time. There are, of course, some corrections, but just now I will neglect these corrections. This is, in fact, very simple. Not a very complicated equation. As I explained to you Jukka Runakara will later send you all these slides. All right. So these yellow circle quantities are determined or obtained from the measurement equipment or from the analysis program. This one. But this is from the data obtained from radionuclide libraries. But there are a lot of different libraries. So, which one should be used in the analysis? It's a very important question because not all libraries are good libraries. So, in fact, the basic emission data have been obtained from scientific publications. However, in very often cases, there are several scientific papers in which emission yields have been reported. But the yields are, or energies are, or maybe a little bit different in each publication. So, how to determine which data is the best? So, the original data, I mean these scientific papers, they have been evaluated by high-level experts, and the final data is gathered in a specific nuclide library. And this is very important because quality of the data is of utmost importance to determine radionuclide activities. So what's the basic data? Okay, basic library data. I will show it soon. Okay, let's go through the decay processes. So mainly we are in this course dealing with alpha or beta decay. Why not gamma decay? There is no gamma decay. You have to understand that. There is gamma emission, so nuclide itself is not decayed when gamma emission happens. So the nuclide stays same. Okay, this list is from the Wikipedia, and this is not a full list. I know that you have studied these kind of things in your universities before, so I will not go through these details. You can do that later when you get these slides. So, what happens? We have a nuclide to be decayed, nuclide X here in this case. It decays via alpha or beta or some other decay process. And here, for example, this alpha 2, beta 2 can go to the base lane. So there is no, what's the word?
Ground level.
Yes, it's a ground level state. Yeah. However, if it doesn't go to the ground level, it will go there very soon by emitting, for example, gammas, X-rays, Auger electrons, or conversion electrons. And these processes are typically very fast. Less than microseconds. Of course, there are exceptions. But this is also very relevant to understand that these processes are really very, very fast. So, from the point of view of the present course, the main decay processes are these. This EC is electron capture. Do you know that? I think most of you knows, but it happens so that a decaying nuclide takes an electron from the electron shells, one of the electrons, and then proton converts to neutrons. And this process generates X-rays because the electrons must be rearranged in a new format. So you have to understand this. I already explained. So there is alpha or beta decay, but no gamma decay. No change of nuclides. Instead, there is gamma emission. So in the previous tables that I showed you in the presentations, so some of these emission yields are normalized to 1. So 1 per decay. However, gamma emissions, they are not normalized. So it may happen that 1 decay can produce, for example, 2 gammas. For example, cobalt 60. It's a typical example. All right. Let's go to the nuclear data. So there are several nuclide libraries such as NSTF. You can click or use that link, NuDAT, and this is the data that radiation metrologists use. This is evaluated data, and I will show you how you can obtain this data. And as I told you, metrologists from International Committee for Radionuclide Metrology recommends of using this data. There are several user interfaces like that. I will show this very soon, not now. It seems to be quite complicated, but it is very easy to use that one. There's NSTEF. You can try to use this link. NuDAT, nuclear data. Oh, this is not valid anymore. So this data is same data basically as in the LARA application that I will show you just now. Is it possible to take it away? I cannot connect to my computer to the net because of some security related things. My organization is very tight in this area. Okay, thanks. All right. Very shortly. You can select the nuclide in question by using this or by writing it down here. I put cesium-137 in the beginning. You can select here what kind of data you want to out, but I just say that, okay, show all data. Let's see what happens. So this is now the data. And you can see here the emissions. So as you know, cesium emits 661 kilo electron volt gammas, but there are also some other gammas too, which are normally not detected by gamma ray spectrometry. But there are emissions of X-rays too. And for example, in this case, if you want to calculate activities to mass, for example, in this case, if I assume 1 becquerel, how much is it in terms of mass? Very low amount, 3 to minus 13 grams. I can put here, or can you suggest some other radionuclide? Which? Cobalt 60. All right. Let's try to use this one. Cobalt. This one. All right. It's maybe it's better to write it down. So all data. So these are the main emission lines coming out. Let's look at the activity to mass conversion. 1 kilobecquerel reverse to this much. If we try to use uranium, for example, uranium 238. So all data. So it's shown here. As you can see, there are no large amount of gammas going out. Close to 50, so the emission intensity is only 0.07. And practically these other gammas, you can neglect these. These are alphas here for MeV. And these are the information of the daughter nuclides, thorium and protactinium. No, very much data. It is because of the protactinium. Let's look at the, okay, and also other nuclides. I will cancel this radioactive chain, so all data, again, now there should be only, not only uranium, let's see, emissions, I select only gamma emissions. What happens now? Why it is showing, so daughter nuclides, cancel this, so all data. Now, this is uranium data. 2 relevant gammas only. And they are not very relevant, in fact. So we have to analyze them by using daughter nuclides. Let's look at the activity to mass conversion. 1 becquerel refers to 80 micrograms. So if you if you need relevant nuclear data, please use this application. And if you are using some other libraries, please compare your libraries to this information.
Can I calculate mass to activity from here?
Sorry?
Mass to activity from here?
Sorry, because of the noise I cannot.
He is asking
Can I calculate?
mass to activity. Yeah.
Let's do it this way. I haven't tested this one. Mass, 1 grams. What happens? Oh. Very handy tool.
Sir, one more question. What's there after the intensity? If you talk of that energy, 49.55 kg in the table.
Yes.
49.55. What is there in the bracket? Is it uncertainty or something?
This is the uncertainty. This is
Uncertainty.
yeah. This is the specific case how to express the uncertainties. It's not. I think it's no. Ah, there. Okay, it's functioning. Thanks. So it's a normal. Well, it depends what is normal, but in that case, 0.0697 plus minus 0.06 0.26. So it's a little bit strange way to express uncertainties, but all right, this is my presentation.